morning, everyone. As I had said, my role was to set up essential perturbation theory and discuss the origin of perturbations during inflation so that Cristiano can go ahead and discuss the formation of black holes in the early universe. We discussed the need for inflation, how inflation is driven with scalar fields. We discussed the type of perturbations that we encounter, and we focused on the scalar and tensor perturbations. And we discussed the equations of motion governing the perturbations. Let me just remind you a few points. We had these scalar perturbations. There were just two of them. And if you don't have anisotropic stresses in the early universe, that is delta Ti, the spatial part is diagonal. There is only a delta P, delta Ij. Then this phi is equal to psi. These phi and psi are often referred to as the Bardeen potentials. Remember, we are working in a specific gauge. There are two scalar degrees of freedom still available with the transformations. We did not worry about it. We chose them to be something and fix the gauge. And we saw that in the absence of anisotropic stresses, there is only one quantity, phi, that we need to follow in the early universe. Please note, I'm talking about a universe post-inflation. During inflation, this delta T mu should correspond to that of a scalar field. We'll come to that in a minute. We haven't talked about the generation and the evolution of perturbations during inflation. We are talking about post-inflation. And we have phi equal to psi, and you arrived at this Bardeen equation. And it was a matter of solving for them. And we carried out a change of variable, okay? I'll come to that. I'll come to curvature perturbation in a minute. We carried out a change of variable and we discussed the solution. What I want you to understand is that these are super Hubble solution. There are two possibilities. One is a growing mode. The growing mode is actually a constant, and the other is a decaying mode. And we ignored the decaying mode, saying that if you retain a non-zero value of CD of K due to some initial condition, the perturbations will be extremely large at very early times. And that will even lead to a violation of the perturbation theory, and therefore we have to assume that these are not present. And please note again, in the early universe, but sufficiently late times post-inflation, and these solutions are valid on super Hubble scales. I will just go to this picture. So this is inflation, end of inflation. We are talking about solutions during the radiation-dominated era, or even the matter-dominated era that comes later, and those solutions are valid on super Hubble scales, and over those scales, phi is roughly a constant. There is a small jump as you go from the radiation to the matter-dominated epoch. Now we need to turn to the generation of perturbations. That is, here the perturbations are generated. Until this epoch, during this epoch, until this time, we are going to assume that inflation is driven by the scalar field, and the perturbations are induced by the fluctuations in the scalar field. So all we need to do is that we need to go back to the scalar equations. Instead of a source, which is we assume to be some hydrodynamical source, we are going to assume that this corresponds to the perturbations in the stress energy tensor of a scalar field. What I did not do, I should have completed yesterday, is to discuss the corresponding equation of motion for the tensor perturbations. Let me just go there. So we discuss, no, I've gone a little ahead. So until this point, we talked about the scalar perturbations. And remember, I introduced this object called the curvature perturbation, right? Which, as I mentioned, reflects the extent of deviation from spatial flatness induced by the perturbation, and hence the name. So we need to also discuss the tensor perturbations. And remember, because of the decomposition theorem, we can study them separately. We can study the evolution of the scalar perturbation separately with the, and the tensor perturbation separately. We had something called script ij that has been called as gamma ij here, right? It appears one in the spatial part of the metric, and that is transverse and traceless. Gamma I is 0 and di gamma ij is 0. And all you need to do is as follows. You need to take this metric and plug in the first order Einstein's equation. There are no tensor sources present. okay, during inflation or even during most of the situations involving in hydrodynamical situations, post-inflation, okay, that I meant radiation or matter-dominated universes, you can ignore the sources. Well, there can be non-trivial sources. If you have some primordial magnetic fields, they can source the tensor perturbations. We are assuming they are not present, and they are certainly not present during inflation. And in such a case, if you calculate the delta Gij, the perturbed Einstein tensor, you can show if you impose the transverse and traceless conditions, these components, only these components are present, and you can set that to 0 because there are no sources present, and therefore that's all there is, the equation of motion governing the tensor perturbations. And if you consider modes, these are linear perturbations, so I can Fourier decompose these tensor perturbations just like I Fourier decompose any linear perturbation, and all that will happen is that there will be a k present, right, and this nabla squared will be replaced by minus k squared as we will encounter as we proceed. Now we need to turn to the origin of these perturbations. As I mentioned, these perturbations are generated during inflation. To repeat, until now we have talked about the evolution of the perturbations post-inflation, and we are able to get solutions in the super Hubble regime. And the reason, and we need to determine this quantity called Cg of k, which I mentioned has to be predicted by or suggested by an earlier epoch, which is inflation. So let's focus on the scalar perturbations first. Tensor perturbations are relatively straightforward. What do I need to do? All that changes is the source on the right hand side. The delta G mu nu remains the same, capital G mu nu and small g mu nu. We have these phi and psi, right? Just like I had, when you had a hydrodynamical source. But here, there is no assumptions to be made. If you are given a canonical scalar field, I can calculate all these guys exactly. And if you recall, I mentioned that, there will be a delta rho, there will be a delta p, and there will be some delta q which corresponds to velocity, and that delta phi, the perturbations in the scalar field essentially plays the role, and you can construct a velocity out of that, okay, and the delta p and the delta rho and can be expressed in terms of delta phi, and of course the body potential appears, and given the stress energy tensor of the scalar field, you can immediately show that delta Ti tropic stress is present. And hence, what you can do is that you can combine the 0, 0 and the Ij Einstein's equations, okay, to and what happens is that, why is there a disturbance? Okay, all right, I'll just proceed, okay. So, I will arrive at this equation governing the body in potential. The non-adiabatic pressure perturbation. Here, since everything is determined in terms of delta phi, you can construct from the body equation by comparing this with the equation that we have. What is delta P and A, and what you find in this case is that it is proportional to nabla squared phi, where Ca is essentially P dot by rho dot, and P and rho, background P and rho plus V, and P phi dot squared by 2 minus V that we had talked earlier. And some gauges are better than others. Maybe Cristiano may comment about it in his lectures, okay. It just happens to be an extremely convenient gauge. So now that the mic is working fine, let's go back to this where we left off. So what do we have? We know what this quantity is, okay, and therefore we arrive at this equation of motion for the curvature perturbation. During inflation, please understand, this equation is valid during inflation when the source consists of a single canonical scalar field. And what do you find? Remember, K being very small, K in fact being much smaller than AH. K by A is the physical wave number, okay, and remember the super Hubble regime. K being much, much less than AH is the super-Hubble regime. Okay? The other limit is the sub-Hubble regime. In such a case, essentially K is small, and what you find is that Rk prime is nearly a constant. So in other words, the curvature perturbation is conserved on super-Hubble scales during inflation and post-inflation as well, if the delta P and A is very small, okay? And that is why the curvature perturbation is a very useful tool. And it is for this reason, what we do is that we arrive at the equation of motion governing the curvature perturbation. All you need to do is that take one more derivative, go back and make this equation, make use of this equation, and what you obtain is a curvature perturbation, equation of motion governing the curvature perturbation. If you recall the equation of motion governing the tensor perturbations, it was very similar in nature, but in contrast to tensors where the z was replaced by a, the scale factor, we have z. What is z? This is an important quantity. It not only contains a, in situation where phi dot behaves like h, z is proportional to a. There are some simple scenarios that can happen if you have power law inflation. But in general, phi dot by h also will depend on time. Okay? The ratio will depend on time. And what essentially will happen is that the behavior of z will determine the behavior of the curvature perturbation. And you may ask, where does my inflationary model go in? Well, remember, inflationary, in order to understand the dynamics during inflation, you need to solve the first Friedmann equation and the equation of motion governing the scalar field simultaneously. And these solutions will give you the behavior of phi and script and h, and you plug them in, determine z, plug this expression in z, and then you need solve this differential equation. And of course, when you want to solve these differential equations, you need to impose some initial conditions. How do we impose these initial conditions? Well, I have been repeatedly saying that these perturbations are generated due to fluctuations in the scalar field. In certain gauges, what you can show is that R is actually proportional to the fluctuation in the scalar field. And this point in mind, what we do is that we essentially elevate R itself as a quantum variable, and it is a quantum field essentially, and you can decompose R in terms of the creation and annihilation operators as you will do with any scalar field, for instance. And what do you have? If you plug this R decomposition in this quantity here, what you have done is that you will arrive at these equations of motion governing this variable fk, which are essentially the scalar mode functions, and they have this equations. They satisfy this equation. Again, what you need to do is that given an inflationary model, you need to determine phi dot and h either analytically or numerically, and then construct z. You need to know what is z prime by z, and then plug it in and solve for f and arrive at the behavior of the modes. And one of the observable quantities that is of interest is the scalar power spectrum, and there is essentially the two-point function of the curvature perturbation in Fourier space. Remember, Rk is a quantum variable, so the expectation value is evaluated in some given state, and often we evaluate in something called the vacuum state, okay? And for certain reason, under certain conditions, it's referred to as the Bunch-Davies vacuum. I'll clarify in a slide or two later. And what you find is that this Ak that appears here, under certain conditions for f of k, there is a state O which kills the annihilation operator, kills that state, and that state for certain conditions on fk is known as the Bunch-Davies vacuum. If you substitute this decomposition and evaluate the expectation value in this vacuum state, what you obtain is this power spectrum that you have here, and this is the scalar power spectrum. And note the right hand side fk depends on time, right? Fk is a solution to this differential equation which depends on the inflationary model at hand, but on the left hand side I haven't indicated the time dependence. What you do is that you evaluate the spectra at sufficiently late times when the modes are well outside the Hubble radius. You should have in the back of your mind this picture that I have plotted repeatedly. You have the Hubble scale during inflation, you have an epoch of radiation domination. This is H, this is inflation, this is radiation domination. This corresponds to the end of inflation. What we are plotting is logarithm of the physical wavelength and logarithm of the Hubble radius, which I have called as dH. This is essentially H inverse. And remember, the modes leave the Hubble radius they are inside the Hubble radius at some early times, and they are on super Hubble scales here. This is the time of Hubble exit. And what you evaluate is, when the modes are well outside the Hubble radius or at the end of inflation. Let me call this some eta E, corresponding to the end of inflation. And what you find is that on super Hubble scales, remember, Rk prime was proportional to k squared when you have scalar field, and they become constant. I will illustrate this with some specific plots as we proceed. So you can evaluate the spectrum either on super Hubble scales, or if you have very non-trivial dynamics during the later stages of inflation, it is better that you evaluate at the end of inflation. So the time is not indicated with the assumption that you either evaluate them when the modes have so-called frozen on super Hubble scales, or preferably you evaluate the spectrum at the end of inflation. That is, as far as the scalar perturbations are concerned. We can do the same thing with the tensor perturbations. And remember, you had an equation like this earlier. We had arrived at the equations of motion governing the tensor perturbation in the absence of sources. In the same manner as the curvature perturbation, you can elevate the gamma ij that you had to be a quantum operator. You can decompose those modes using a polarization tensor that describes the gravitational waves, the two modes of polarization that we have in Einsteinian gravity, and you can decompose them in terms of some bk and bk lambda, bk dagger lambda. Lambda denotes the two states of polarization. Again, if you substitute this decomposition in the equation of motion that you had earlier, you will arrive at an equation of motion governing the tensor perturbation. In contrast to the scalar perturbations, the tensor perturbations do not depend on the scalar field in any manner. They depend only on the scale factor. The scale factor the scalar field influences the scale factor, and the scale factor in turn determines the dynamics of the tensor perturbations. And you can define, these are just the polarization, some essential properties of the polarization tensor. I have included them for the sake of completeness. I'm sure you are familiar with this. You can decompose the plus and minus plus and cross polarization in terms of an orthogonal basis, and they satisfy certain normalization conditions. And you can define the tensor power spectrum in this manner. It is essentially a two-point correlation function of the modes of the curvature, of the tensor perturbation in Fourier space. And you can write it in this fashion, where gk are these mode functions that appear here. And once you have, again, as in the case of scalars, given a of eta, you can solve for these gk's and plug it in this expression, evaluate the spectrum, just like you did for the scalar power spectrum at late times, when the modes are, you impose the initial conditions. I will talk about the initial conditions soon. You impose these initial conditions when the modes are well inside the Hubble radius, that is when k by ah is much, much greater than 1. You evaluate the spectrum when the modes are well outside, when k by ah is much, much smaller than 1. Now, remember, we talked about slow roll inflation, okay? And I discussed a few models, and yesterday I didn't have my Mathematica code working. From what I understand, it works now. Let me see whether I was told it's open. Right. This is the simpler one. So it's a simple quadratic potential, right? Okay, I need to, okay. So I have just integrated, there is a quadratic potential which is defined here, okay. And I'm integrating, in terms of, all you need to do is that for efficient integration, you need to work in terms of E folds as the independent variable, which I have called as N1 here, okay. And here is the analytical solution that we had obtained for the case of a quadratic potential. And here is a comparison of the slow roll result and the analytical solution. This is the slow roll. The dotted one is the slow roll result, and the exact numerical solution is the red line. And as you can imagine, they match fairly well until close to the end of inflation. So what you do is that you start at some initial value. I've chosen an initial value which is determined by this relation that we had earlier. By this relation that we had obtained in a discussion yesterday for the case of the so-called large field models. And then you can calculate the behavior of the Hubble radius. I have done that here. And what you find is that for most of the period of inflation, the Hubble scale, or the inverse of it, which is the Hubble radius, remains roughly the constant. I mean, for almost until 60 e-folds or so, it changes only by a factor of 2. And you can estimate the slow roll parameter, okay, and see where inflation ends, right? So here is the behavior of the first slow roll parameter. It remains very small, about 10 power minus 2 or small, and then it slowly rises, leading to an end of inflation. And you can estimate the next slow roll parameter, okay? Next slow roll parameter here, it remains small, the second slow roll parameter, and then it rises, and it becomes large only close to the end of inflation. And you can determine where inflation ends by setting epsilon 1 to be 1. That's what this is. And you find for the initial conditions, inflation ends here. Okay? And we will come to the evaluation of the perturbations once I discuss the generation of perturbations during inflation. So we need to calculate the scalar and tensor power spectra in slow roll inflation. What you essentially need to do is that you have this f subscript j and g subscript j, which are the scalar and tensor mode functions, and you need to solve them, for a given z of eta or a of eta. It is useful to introduce a quantity called the Mukhanov-Sasaki variable. There is a Mukhanov-Sasaki variable for scalars and a Mukhanov-Sasaki variable for tensors. We had fk, which was the scalar mode function which satisfied a given differential equation. I'm going to write this as vk divided by z. Z is the quantity that I have already introduced earlier. Then what you find is that this vk reduces to an equation of this form. It is convenient because it is essentially a time-dependent oscillator that you have. And in terms of the power spectrum can be expressed in this form. Now, what happens is that in the sub-Hubble domain, remember I have been saying the initial conditions are imposed in the sub-Hubble domain. This is the domain where k squared is much larger than anything else. K is large when the wavelengths are small, right? In such a case, evidently I can ignore this and Vk will satisfy a simple solution like this, which is essentially what you will have, what you have in Minkowski spacetime. So when the wavelength of the perturbations are much smaller than the curvature scale, which is set by z double prime by z, essentially you have oscillatory solutions, and these are your initial conditions for the perturbations. This corresponds to assuming that the perturbations are in something known as the Bunch-Davies vacuum. With these initial conditions, for a given z of eta, you have to solve for fk of eta and evaluate them until late times, evolve them until late times and evaluate the perturbations close to the end of inflation. This is the task ahead. So as I mentioned, you impose the initial conditions here, evolve them and evaluate the perturbations close to the end of inflation. So epsilon 1, epsilon 2, epsilon 3, etc., the slow roll parameters, it's a simple exercise to write this quantity z double prime by z, which appeared in the Mukhanov equation of motion governing the Mukhanov-Sasaki variable in terms of the slow roll parameters. And what you can do is that in the slow roll approximation, you can use the definition of the first slow roll parameter to arrive at this expression. You are just integrating the equation by parts, where script h, remember, is the so-called conformal Hubble parameter. It is just a times the Hubble parameter. So you can, these are higher order in the slow roll parameters. We are working at the leading order in the slow roll parameters. Essentially, it contains products of slow roll parameters. We can ignore them. And therefore, the h is given in terms of eta and the slow roll parameter by this term here. You take this expression. Notice it is only these terms that are present. There are higher orders in the slow roll parameters. Ignore them. And you can arrive at a nice expression for z double prime by z given by this expression. Remember the equation of motion solved. We need to solve this equation. What you essentially have is some constant divided by 1 over eta squared. Okay? It so happens it can be solved in terms of Bessel functions. And you will encounter these Bessel functions very often when you try to solve for perturbations in the early universe or even in the late universe. And since you need to impose oscillatory type of initial conditions, so it's a linear combination of Bessel functions which are known as the Hankel functions, the mode functions that satisfy this initial conditions, which says that at very early times they should behave as e power minus I k eta, the solutions happen to be the Hankel functions of the first kind. That's all there is to it. Where is the information about the model buried? Remember, you have epsilon 1 and epsilon 2. We are often interested in modes which are on large scales, which leave the Hubble radius at extremely early times, okay? And where epsilon 1 and epsilon 2 are nearly a constant in slow roll models. Remember the plot of the epsilon 1 I showed in the quadratic potential. It remained small until late times when it started rising, leading to an end of inflation. So the new S here is determined by these quantities, epsilon 1 and epsilon 2, okay, at very early times. And therefore, you have the Hankel functions. So what do you do? You take this Hankel function, plug it in this expression, take the limit at corresponds to late times, which corresponds to eta going to 0, that corresponds to late limit. So you essentially have to use some series expansion of the Hankel function to arrive at this, to arrive at the power spectrum. Okay, this is the power spectrum. It's just the rest is a matter of algebra. And what you find is that I will talk about the earlier slide in a minute. Bear with me. Mathematically, that is all you need to do. And you arrive at an amplitude which is essentially h squared. Remember, h was almost a constant. Remember, only after 50 E-fold, it fell by a factor of 2. Otherwise, it's largely a constant. Epsilon 1 is the value of parameter at early times when the modes of interest leave the Hubble radius, and this is the complete spectrum in slow roll inflation. And you can, if you want to check where the k dependence arises, it arises very weakly as a logarithmic factor here. And one of the observable quantities other than the amplitude of the power spectrum is what is known as the scalar spectral index. It is constrained remarkably well, and it is defined by this expression. Given this expression, you can immediately calculate what is ns minus 1. You find that ns is 1 minus 2 epsilon 1 minus 2 epsilon 2. And remember, epsilon 1 and epsilon 2 are slow roll parameters. They are supposed to be very small. So this is often you hear the term that slow roll inflation leads to a nearly scale invariant scalar power spectrum. And in fact, what you will find, is epsilon 1 has to be smaller than a certain quantity because it leads to a certain value for the tensor to scalar ratio, and therefore ns is largely, according to the current observations, determined by epsilon 2. So I had said I will say a few remarks about this. What essentially happens is as follows. What has been plotted is the amplitude of the real and the imaginary parts of the curvature perturbations. I have solved it numerically. And in this particular case, the mode leaves the Hubble radius around this time. Okay, around this time. So what happens is that the modes are inside the Hubble radius, and how will they behave? They will oscillate. Decreasing amplitude, as you can see, they oscillate with decreasing amplitude, and once they leave the Hubble radius, somewhere here, they become constant. Remember, we had generically shown that on super Hubble scales, if you have slow roll inflation, Rk will be a constant, and that is essentially what you see. You can evaluate the spectrum here, or you evaluate the spectrum much later times, and you will get the same spectrum. And so, the bottom line is that the amplitude of the scalar perturbations is determined by h squared by epsilon 1. Okay, the smaller the epsilon 1, the larger the scalar amplitude, the larger the h, the larger the scalar amplitude, and the ns is given by this expression, the scalar spectral index. And one finds that, in the models that one often considers epsilon 2, epsilon 1 is always positive, epsilon 2 happens to be positive as well, and therefore you will have a red tilt. In other words, you will have more power on large scales or small k, and small power, lower power on large k or small scales. This is as far as the scalar perturbations are concerned. We need to move to the tensor perturbations. And just as we introduced the Mukhanov-Sasaki variable for the scalar perturbations, you can introduce a Mukhanov-Sasaki variable for the tensor perturbation, and you often introduce a factor of, root MPL, because if you look at the action governing this tensor perturbations, there is 1 over 16 pi g that arises from Einstein-Hilbert action, and therefore it is conventional to introduce this quantity here. And if you define this, Mukhanov through this relation, uk by a. uk is the Mukhanov-Sasaki variable describing the tensor perturbations. It should not come as a surprise. It will reduce to an equation of this form. Again, what do? You impose the initial conditions when k is much, much greater than the square root of a double prime by a, which essentially corresponds to the modes being well inside the Hubble radius. You impose these Bunch-Davies initial conditions that I have already referred to, and you evaluate the spectrum given by this expression. All I have done is that substitute this expression for gk here, and you have this expression. You evaluate the spectrum at late times. And it should not come as a surprise that, you find, even in slow roll inflation, this is an exact expression, whether it is slow roll or otherwise. In slow roll inflation, as we have already seen, h is given by this expression. Therefore, you can immediately calculate a double prime by a, modulo some constants, it is 1 over eta squared, and the solution to this differential equation involves Bessel functions. You choose some initial conditions which helps you arrive at the solution to be some Hankel function. The index is different because evidently a double prime by a is different from z double prime by z, and therefore what you have is that index determines the amplitude as well as the shape of the tensor power spectrum. So plug this expression here, take the small eta limit which corresponds to late times in slow roll inflation, and what you arrive, it is a power spectrum. You should contrast this power spectrum with what you obtain for the case of scalars. Remember, the scalars contain h squared by epsilon 1, and epsilon 1 is model dependent. H squared is proportional to rho according to the Friedmann equation, right? So if the tensors depend only on h squared. So if I know the amplitude of the tensor perturbation, I know the scale of inflation. That's why the tensor perturbations are important, and you can immediately read off the tensor spectral. It is just a convention. Here you define with ns minus 1, and here you define as nt, which is d log pt by dk, and you can immediately read off that the tensor spectral tilt is minus 2 epsilon 1. Okay, and in other words, it's red. For instance, if you see blue spectral tilt, you have a conflict with inflation. Slow roll inflation suggests, unless you do something non-trivial, slow roll inflation will lead to only a red spectral tilt for the tensor power spectrum. One of the observable quantities I will talk about very soon is something called the tensor to scalar ratio. What it is you take this amplitude, right, of the tensors and divide that by this amplitude. Don't worry about the scale dependence for now. You divide by this tensor scalar amplitude, and what you obtain is that, as you can imagine, it only contains epsilon 1. It is 16 epsilon 1. And there is something called consistency relation. Imagine you are able to see the imprints of the tensors. I will talk about where you can see the imprints of the tensors. You are able to not only see the amplitude of the tensors, you are also able to decipher the shape of the tensor power spectrum. Then you know R, you know NT, and if this condition is satisfied, what you essentially have is an epoch of slow roll inflation. But we are yet to see tensors, and therefore this result is just, this relation is just a theoretical relation as of now. And there is one particular example it is convenient to discuss. It is the so-called de Sitter limit. There is a pathology associated with taking the de Sitter limit as far as scalar perturbations are concerned. You go stare at the energy for expression for the energy and pressure for the of scalar field. It is phi dot squared by v and phi dot squared by 2 plus v and phi dot squared by 2 minus v. So the de Sitter limit corresponds to phi dot equal to 0, where p equal to minus rho. But phi dot equal to 0, remember your z is a phi dot by h, the z that determine the scalar perturbations. So that vanishes and poses certain trouble as far as the scalar perturbations are concerned. There is no such issue discussing de Sitter limit in the case of tensor perturbations. You have the scale factor, you can substitute that, and you can immediately arrive at the solution to u of k. It's a simple solution. It so happens when you set epsilon equal to 0, you have nu t equal to 3 by 2. And if you know your Bessel functions or Hankel function, h half and h 3 by 2 have simple forms, and that is what you see here. And this solution is easy to obtain. You can take the late time limit and you can show in d zeta inflation the tensor power spectrum is strictly scale invariant. What you can do, and what we will indeed do, is that, instead of dealing with a more non-trivial Hankel functions in the case of tensors, in the case of scalars, what we will do is that we will ignore these, assume this Hankel function to be of the, to be 3 by 2, Hankel function corresponding to 3 by 2, but we will retain a factor of 1 over root epsilon. That is, I can write the Vk as everything essentially the same. There is something wrong here. This should not be k eta, it's 2k, okay? And you can introduce a 1 over root epsilon 1, and assume that it describes the scalar perturbations in slow roll inflation, particularly when it is remarkably close to d zeta inflation. So I will use those solutions as we proceed. So what have we learned? We have learned the following. Let me quickly summarize. There is a scalar amplitude which is given by this. The scalar spectral interest is given by this, okay? So we know the scalar amplitude, as I will mention, very well from the CMB observations. We have strong constraints on the scalar spectral index. We are yet to see imprints of the tensor perturbations. In other words, we are far from determining what is NT is, because we don't even know their amplitude. So observationally, our immediate interest is to constrain the tensor to scalar ratio. What is the amplitude of the tensor? We know the scalar amplitude so well, we would like to constrain what NS is. As we will see a couple of slides later, that NS is well constrained, and there are upper bounds tensor to scalar ratio R. So now let's discuss quickly the constraints on inflation from the CMB data, and these are the original fluctuations seen in the CMB seen by Kobe. Over the last 30 years, they have been measured to greater and greater precision, initially by WMAP and later by Planck. And you have, when you compare your primordial power spectra with the CMB observations, for reasons that I have just discussed, you assume a simple form. Okay? You assume that the primordial scalar power spectrum is given by this. Evidently, this is the scalar amplitude, which was proportional to h squared by epsilon 1, if you recall. And this is the tensor amplitude, and this is the scalar spectral index, and this is the tensor spectral index. If you evaluate the spectrum in slow roll inflation, and if you evaluate over a wide range of scales, maybe this is a good time for me to just use the Mathematica file, okay? I really am short on time to explain this in detail. I will leave this file with you. It is a simple file which you can use, and I will just show you the result that I have already calculated, okay? So this is the actual evolution of the scalar and tensor perturbations. This happens to be the scalar perturbation. Notice, I have plotted the real and imaginary part, absolute values. They oscillate, and somewhere Hubble exit occurs, and thereafter their amplitude freezes. And you can go on to calculate the scalar and tensor power spectra. This is the scalar power spectra. There is a small tilt. The amplitude doesn't change significantly. On the larger scale, I have ensured, in fact, it is Kobe normalized. There is something called a pivot scale at which the amplitude happens to be Kobe normalized. This is something called Kobe normalization. Okay, I will talk about it very soon. It's something like 2 times 10 power minus 9. And what you arrive at in the quadratic potential, I'll just show the final result, is the scalar. This is the scalar power spectrum in blue and the tensor power spectrum in red. And over scales, large scales, the ratio is of the order of 0.1 or so. Okay, so let me go back to my slides now. So we are interested in, as I already mentioned, we know this well. We are yet to determine this. We are interested in R and we are interested in NS. And very quickly, what happens is that given a primordial scalar and tensor power spectra, you can calculate the CLs. CMB is polarized, it's photons, it's polarized, and you can divide them into 2 modes of polarization, the E and the B. It so happens that the B modes are generated only by the tensors. Well, if you consider linear perturbation theory, but there can be something non-linear called gravitational lensing that can induce the B modes. Okay? So if you are able to see this blue spectrum in the B mode on scales where, on multipoles where the lensing does not affect, you can see the primordial signatures. We have been able to measure the T spectrum fairly well, as I will display, and you have also been able to measure some correlations such as TE and TB, or TEE and BB as well. This is just the TT result, okay? And what has been plotted are the data points here, and the curve corresponds to a primordial, nearly scale invariant power spectrum as indicated earlier. And what are the constraints? What you find is as follows. The primordial spectral tilt, the scalar spectral index NS, happens to be very close to 0.965 or so. So if you have an inflationary model that leads to a primordial spectral tilt of 0.965, then your model is remarkably consistent with the data. What about the tensors? I mentioned that we are yet to see imprints of the tensors, but the latest, well, not the latest, this slightly older constraint suggests R is less than 0.05 or so. I just mentioned in a quadratic potential, the scalar to tensor ratio, the tensor to scalar ratio was 0.1 or so, which means they are somewhere here, okay? R squared, phi squared model is somewhere here. It is ruled out by the data. What is one of the most popular models today that fits the data well is the Starobinsky model, the R plus R squared model, which can be, you can carry out something known as a conformal transformation and reduce to a Einsteinian gravity model plus a potential that I had discussed earlier that happens to be remarkably consistent with the data. It leads to a tensor to scalar ratio of few times 10 power minus 3 and an NS of about 0.96 or so. So this is, remember, I had told you that the gravitational lensing also leads to this B mode polarization. These are the constraints on the B mode polarization, okay, from gravitational lensing. These are all seen on, large scales or on large multipoles. But remember, we want to see them here in order to detect the primordial tensor modes. The latest constraints from the CMB on the tensor to scalar ratio comes from the bisect Keck data, and that happens to be 0.036 compared to Planck. It has come down to some level. And what is the prospects of observing this? This is a forthcoming mission, Japanese mission called Lightbird. And this is the sensitivity. The Cyan curve is the sensitivity of the Lightbird instrument. And this is lensing. So if you have an R of 4 times 10 power minus 3, you may be able to see the signals over the smallest multipoles. And if you are able to see, you are essentially seeing the primordial tensor modes generated, during inflation. And if you know this, and there are no other contamination, due to other effects during inflation, then you know the scale of inflation. So I have about 40 minutes. So as I said, I would like to keep this talk self-contained. So I'm just going to discuss, before I come to non-trivial scenarios involving what is known as an epoch of ultra-slow roll inflation, which can lead to enhanced power on small scales. I'll just, give some indication of what happens to these primordial tensor modes that are generated during inflation. Well, the gravitational waves are observed for a wide range of frequencies. I have been talking about the imprints on the CMB. I just talked about the prospects of measuring it. And I'm sure, there have been significant discussions about, about that detection in the LIGO range of frequency, largely from astrophysical sources. But you have to remember that the cosmological sources, produce gravitational waves. Even the primary gravitational waves generated from the quantum vacuum are generated over a wide range of frequencies. All the scales, here is where the cosmological scales leave the Hubble radius. Even the smallest scales, this corresponds to a scale of about 10 power minus 4 megaparsec inverse, corresponding to a Hubble radius today. And that lies somewhere here in terms of frequencies. And the other extreme corresponds to the smaller scale, which will leave the Hubble radius about 60 e-folds after the 10 power minus 4 leaves the Hubble radius, and that can be something like 10 power 19 or 10 power 20 megaparsec inverse, and they can lie in the gigahertz range of frequencies. It can lie here. Okay, so the primordial gravitational waves are generated everywhere, okay, or all range of frequencies. It just depends on the dynamics during the early stages. And of course, there is a proposed LISA mission to detect gravitational waves over intermediate range of frequencies, and I'm sure you may have heard that the pulsar timing arrays have seen a stochastic gravitational wave background, and there is considerable interest in trying to understand what is the source of these gravitational waves. So what essentially happens is as follows. Remember I talked about how the CMB comes to us, decouples from matter around this epoch and travels to us freely, and that is what we observe as the CMB, and we see the anisotropies, and from those observations we are able to determine what happened behind this window even during the epoch of inflation. In contrast to the photons, the gravitational waves interact even more weakly with the matter present, okay, and as a result, in principle, the gravitational waves generated during inflation that I have been talking about, the tensor power spectrum, the constraints from the CMB occurs only on large scales, okay, scales of about, where is the chalk piece? Over these large scales, only over these large scales. I will talk about these scales, but on smaller scales, there are no constraints. I will emphasize this point as we proceed. And in other words, there is only over these scales. On these scales, there are no constraints yet on primordial gravitational waves unless you use the sensitivity of one or more of these instruments. And as a result, all these gravitational waves can travel freely, and you can in principle detect them over these wide range of frequencies. And what you can do is that one of the observable quantities is something known as the spectral density of gravitational waves. It is the energy density per logarithmic mode present in the gravitational waves, whatever the source is. Okay? And if you have a gamma ij that describes gravitational waves, you can construct such energy density associated with it. You can discuss it in some standard textbooks and some of the standard papers, and it is given by this expression. And you can, remember I had an expression for gammas, for instance, in terms of the Fourier modes gk, right, in terms of the Fourier mode gk. And we have talked about solving for gk during inflation, and I indicated as to how it's extremely simple to solve in de Sitter inflation, okay. And you can plug that decomposition and you have an array expression for the spectral energy density of gravitational waves. I can calculate this at the end of inflation over a wide range of scales. The CMB, again, to emphasize, constraints only over these scales, but you can in principle evaluate this over a wide range of scale and ask whether such a gravitational wave corresponds to a tensor to scalar ratio of 0.01, what will it correspond to on these scales? And that is what we are trying to understand, okay? So you have the energy density, you have the spectral energy density of gravitational waves. What you are interested in, the so-called dimensionless spectral energy density of gravitational waves. It is just the spectral density divided by the corresponding critical density, and this is at any given time eta, evaluated during the early stages when all the modes have re-entered the Hubble radius. Remember, they leave the Hubble radius during inflation if they are generated, the primary gravitational wave generated, and they re-enter the Hubble radius. You can evaluate them here. And when these gravitational waves are well inside the Hubble radius, they behave like radiation. And as a result, the energy density, that dimensionless spectral energy density of gravitational waves can be related to the energy density, dimensionless energy density of radiation today, which is omega r h squared. And of course, all the information about what generates these gravitational waves lies buried here. In other words, you need to calculate this quantity. They were generated during inflation. You need to evolve them to, due to the epoch of radiation domination. Or if there is an intermediate epoch like reheating, you have to allow, you have to evolve those gravitational waves across these epochs and evaluate the spectrum somewhere here when they are well inside the Hubble radius. You plug them in And then the energy density of gravitational waves today is given by this expression. So you can solve that. For instance, during the epoch of radiation domination, the scale factor is given by this expression. And A double prime by A is 0. It's trivial to solve. You can determine these constants and so on. And if you have some intermediate epoch during this, you need to evolve them, match them. I mean, this is away from my goal, so I'm just going to be brief. And if you want to remember, I've been talking in terms of wave numbers, okay, and I will continue to talk in terms of wave numbers as far as the primordial spectrum are concerned. But if you're looking at omega GW, the spectral energy density of gravitational waves, it's plotted often in terms of, indicated often in terms of frequencies. I mean, the LIGO guys talk in terms of frequency, not in terms of wave number, and this is the conversion. For instance, something like 10 power 7 megaparsec, 10 power 7 megaparsec inverse, 10 power 6 megaparsec inverse corresponds to f of the nanohertz range of frequency that is of interest in the PTA. So you can ask, if you introduce an epoch of reheating, what is the energy density, the spectral energy density of gravitational waves? If you did not have reheating, you had a transition from inflation to radiation domination, what essentially happened is that this will lie at this range, okay? And this will be of the order of 10 power minus 17 or so, okay? A tensor to scalar ratio of about 10 power minus 2, 10 power minus 3 leads to omega GW today of about 10 power minus 17. If you have an epoch of reheating, non-trivial epoch, they can have a small, particularly the equation of state during this reheating, if it is greater than 1/3, they can lead to a blue tilt, and that's one hope of, possibly having adequate strings of primary gravitational waves that are comparable to the sensitivities of the various gravitational wave detectors. This was a set of slides I thought I will just discuss because it's a school pertaining to gravitational waves. But we move on to my main target in the last 30 minutes, namely, why do we need to consider primordial black holes? Well, it's as follows. This is, again, if you are students working in the context of gravitational waves, you know this catalog very well. These are the various black hole binaries that have been detected through gravitational waves, or rather, gravitational waves from these sources have been detected from these mergers of these binary black holes. When these objects started being detected, what people found is that they were often in fairly high masses of solar masses. Astrophysicists naively imagine that the masses of these objects will not be so high, a couple of hundred, etc. They may have been at tens of solar masses, or the other extreme when you have galactic black holes. But it came as a surprise to people that there were many, many reasonably heavy binary black holes that were merging. And there was a interest to examine whether, instead of astrophysical black holes, whether any of them could have formed in the early universe. What does it mean? Well, you have these modes here, right? They re-enter the Hubble radius at different times. If you have a scenario where the amplitude of the perturbations are very large, okay, and when they re-enter the Hubble radius, once they are inside the Hubble radius, Newtonian begins to play a role, okay? General relativity is important only when the perturbations are comparable to the Hubble radius, and the Newton gravity will make these higher densities collapse and form black holes. So essentially what happens is as follows. Remember, this is the physical scale, evolution of the physical scale that have been plotted. I've been telling you how it is important that you grow comfortable with the plot of the corresponding co-moving scales. And remember, as far as co-moving scales are concerned, the wavelengths are concerned, they are constant. They don't change with time. The Hubble radius during inflation, remember it's a constant, but the co-moving Hubble radius corresponds to h by a, therefore it has a slope of -1. And I've let you convince yourself that the co-moving Hubble radius during radiation domination has a slope of 2. I had mentioned earlier, as far as the physical Hubble radius is concerned, it has a slope of 0, and during radiation domination it has a slope of slope of +2. You have to divide by a, so this slope becomes -1, from 2 it becomes 1, and it is convenient to consider in terms of these co-moving scales. So what do you have? You have the wavelength of these perturbations. This corresponds to a large scale mode. This corresponds to a small scale mode. The large scale modes are well constrained by the CMB. But the small scale modes, if they have adequate amplitude, they can in principle collapse to form primordial black holes. And the question is, can you form adequate number of primordial black holes such that some of them may be seen by LIGO? What is the strength that you require in order to form a good number of primordial black holes? I will talk about the extent of what is a good number as we proceed. Cristiano will talk about it in further detail. As I have been saying, inflation generates perturbations over a wide range of scales, from something like 10 power 4 megaparsec inverse to scales which are even larger, to wave numbers which are even larger than 10 power 14 megaparsec inverse. So on the larger scales, it is well constrained by the CMB. This is the amplitude or square root of the amplitude of the primordial curvature perturbation. If you want to form good number of black holes, what you need is that this is 10 power minus 5. Something I didn't emphasize, but I hope you have noticed, I mentioned something called an AS, which was the amplitude of the scalar perturbations. It's roughly of the order of 10 power minus 10. You can think of it as delta t by t squared, which is 10 power minus 10. Root of that, I mentioned a word Kobe normalization. Okay? Root of that is 10 power minus 5, between 10 power minus and 10 power minus 4 to be precise. So the amplitude of the curvature perturbation is fixed to be at this value according to the CMB data. But the CMB data is sensitive only to these scales. Something like 10 power minus 4, 10 power minus 5 megaparsec inverse to about 1 megaparsec inverse. And there is some additional data coming in from large scale structure, Lyman alpha, even 21 centimeter physics. Okay? And they all end here at something like 10 power 0 to 10 power 1 megaparsec inverse. Thereafter, there are no constraints. There are absolutely no constraints. Well, there are constraints from spectral distortions. You can speak to me, later. Maybe Cristiano will talk about it briefly. Okay? And there are very little constraints on small scales. So the question is, can I construct scenarios where I have enhanced power? What do I mean by enhanced? The power has to go from, in terms of zeta, from something like 10 power minus 5 to close to 1. And if you can enhance power to these scales to such an extent, then you can form an adequate number of black holes. Black holes are cold, so they can contribute to cold dark matter. And the question of interest is that, can all cold dark matter be constituted of primordial black holes? And if you want to produce enough number of them, as I said, your spectrum has to be nearly scale invariant in order to be consistent with the CMB on large scales, and the power has to rise, and it has to match this power in order to generate adequate number of black holes. How do you achieve that? Well, if you have inflationary models that only permit slow roll, you cannot do that. Essentially what happens is that the inflationary power spectrum, I don't know whether you saw the mathematical code I showed. I didn't show it for a long time, but I tried to evaluate it for a wide range of scales, not only on the CMB scales. I evaluated it even further. It had a red tilt. So the power will start here in order to be consistent with the CMB data. In slow roll inflation, it will keep going down. The power will remain very small on the Kobe normalized value. But if you want to enhance power on large scales, on small scales, then you need deviations from slow roll inflation. And one simple way of achieving this is introducing an epoch of ultra slow roll. I had already mentioned as to how slow roll inflation corresponds to where epsilon 1 is small. Remember, epsilon 1 has to be small, smaller than 1 in order to have inflation. And in many of the scenarios, you realize that if you want to be consistent with the CMB data, epsilon 1 has to be reasonably small, 10 power minus 2 or so. If you have an epoch where epsilon 1 falls drastically, it's not only slow rolling, it is ultra slow rolling, then what we will see is that you can enhance power on small scales to this extent. And that is what I'm trying to explain over the next maybe half a dozen slides. So let's go back to this equation of motion governing the scalar field, right? So what do we want? We want epsilon to be very small. And why so? Remember the scalar power spectrum. Okay? This is not a very correct argument, but it seems to be okay. This is not. Remember how the scalar power spectrum behaves. It behaved as h squared by epsilon 1. Right? If you have slow roll inflation, the smaller the epsilon 1, the higher is the amplitude for a given h. And if epsilon 1 is falling with time, it is actually even better slow roll approximation. But if you have a scenario where epsilon 1 starts going down, and if I use the scalar amplitude as I indicated, it is clear that the scalar power will rise. And that essentially what happens, though this argument has its fallacies. So how do you achieve this enhancement in power? You need this epoch of ultra slow roll inflation. How do you achieve that? Well, all you need is a point of inflection in your potential. That is, if you have a V phi equal to 0, then what essentially happens is that this goes away. You can immediately integrate this equation. Remember, h is a dot by a. And what you can show is that phi dot squared goes as 1 over a cube. I had earlier mentioned as to how, if epsilon 1 is small, the de Sitter approximation, where the scale factor is given by 1 over h eta, h being a constant, is a good approximation. So, if you have ultra slow roll, it is even better approximation because the field is hardly, remember, phi dot equal to 0 corresponds to de Sitter. Phi dot is small is slow roll. So if phi dot is reasonably small, it's reasonably close to de Sitter. If phi dot is smalling, it is even better, even significantly more close to de Sitter. So the de Sitter approximation, where h is a constant, works reasonably well. And what you essentially find is that phi dot goes as 1 over a cube. It falls drastically. I will illustrate with some plots in a slide or two later. Okay? And the epsilon 1 starts falling extremely rapidly. Of course, this is true if V phi is 0, but if you also have V phi to be 0, what essentially happens is that this V phi remains 0 for a sufficiently long time, and you have an extended period of ultra slow roll. But this doesn't mean the slow roll approximation is valid. It's not, in fact. Remember, the slow roll approximation corresponds to the situation where not only epsilon 1 is small, but epsilon 2, epsilon 3 are also small. But you can quickly convince yourself, if epsilon 1 is rapidly decreasing in this fashion, the second slow roll parameter is not small. It's fairly large. Actually, there is a violation of the slow roll approximation. So all those arguments that I had to evaluate the spectrum in the slow roll approximation do not hold true. So what you need is study the effects of ultra slow roll on the primordial power spectrum. I will illustrate with the help of numerical results, how this typically is achieved. So these potentials that I have considered here contain a point of inflection. I will let you work them out. And what essentially happens is that if you had slow roll inflation, as I displayed earlier, epsilon 2 remains small, it constantly rises and goes to 1, leading to an end of inflation in slow roll. And epsilon 2 will do the same. It will be smaller and it will rise, leading to an end of inflation. Let's not worry about this. But in slow roll, ultra slow roll, what essentially happens is that because there is a period where it rapidly falls, you can see in a couple of examples here, epsilon 1 decreases rapidly. And you can see that epsilon 2 becomes large. It's of order -6 or so during this epoch of ultra slow roll. What happens during ultra slow roll? The field velocity becomes extremely small. Right? Phi dot goes as 1 over a cube. And that is displayed here. What has been plotted is the phase portrait. Remember, I talked about the inflationary attractor as to how if you have slow roll inflation, all trajectories will merge towards the attractor. And that is displayed here. There is a gene of slow roll corresponding to this epoch here. But this is the point of inflection. As it approaches the point of inflection, there is hardly any force on the field. In addition, there is friction because of the expansion. As a result, what happens? The velocity of the field, this is the slow roll approximation in dotted line. The slow roll approximation during slow roll is good, but when it is ultra slow rolling, the approximation fails. And in fact, what happens is that the field's velocity, as you can see, decreases rapidly. Somehow it manages to escape the grip of the potential, and it comes down, oscillates, leading to the end of inflation. And as I mentioned earlier, the scalar power spectrum in slow roll is h squared by epsilon 1, right? And the epsilon 1, instead of being constant, has this. If you plot 1 over epsilon 1, how will it look? It will be like this. Instead of going down, 1 over epsilon 1 will come down, go up and come down. And that's how the scalar power spectra, I'll come to this, I'll come to these, oh, okay. I'll plot, that is how the scalar power spectra look. I will, there are a few slides I have to understand the spectra. I have just showing the numerical results. We will try to understand that analytically. So in many of these cases, remember the epsilon 1 went like this, goes down and goes up. The scalar power spectra in contrast goes up and comes down. And notice in some of these cases, you have a nearly scale invariant spectrum on large scales, and the power on small scales is close to 10 power minus 2. By tweaking your parameters, you can ensure that it's as close to as 1. If you cross 1, of course, the perturbation theory becomes violated. Okay, you violate perturbation theory. You want to keep it lower than that. So how do we understand this? So let's try to understand this to some level. Okay, and so this is the picture that I have already explained, these plots. Remember our Fk. Fk is the mode function describing the curvature perturbation. So consider a scenario where the modes already, you have an epoch of ultra slow roll. Keep this in mind. There is an epoch of ultra slow roll. We'll first consider what happens if you had slow roll followed by ultra slow. We'll worry about what happens due to this a little later. It requires a little more algebra. So if you have slow roll, and the modes are on super Hubble scales, what happens to the modes? Okay, what happens to the mode? They will become constant. Actually, as I have been telling you, in the case of the Bardian potential, there are two solutions. There is a growing solution and the decaying solution. Okay, so in the first regime, what you have is that on super Hubble scales, if you are in the slow roll regime, you can write it in this fashion. But remember, if this is on the super Hubble regime, their initial conditions have to be imposed in the sub-Hubble regime from early times. I can take a solution. I know the solution. If it is slow roll, I have already indicated I can use these solutions which are of this form I had indicated earlier. I can choose my Vk of eta to be of this form. E power minus ik eta. So I know the solutions, which means that on super Hubble scales, I know what is Ck and dk. I just have to compare them with this. Now, what do I do? At some time, I bluntly, abruptly change to an epoch of ultra slow roll. What happens during ultra slow roll? We discussed it here, right? Epsilon 1 goes as 1 over a cube. So during slow roll, right? Remember, z is a phi dot by h, right? You can write this as a times root epsilon 1, modulo some constant. In slow roll, this goes as 1 over eta. But during ultra slow roll, because epsilon 1 is a constant, a is de Sitter approximation is good. But during USR, what happens? This is a root epsilon 1, okay? I hope I get everything right. This is 1 over epsilon 1 is a cube, 1 over a, a6, it is a cubed. Root epsilon 1 is 1 over a cubed. So this is proportional to 1 over a squared, okay? All right? I hope I got that right. Okay? So yes, this is proportional to eta squared. Yes, that's correct. Okay? So what you essentially have is, remember, if I have a differential equation, which is k double prime plus k squared minus z double prime by z, Vk equal to 0, right? I had written two solutions. One of them is a constant and the other is, in the context of Bardian potential, it was a decaying mode. I have just, identified these two and determined what is Ck and dk by matching with initial conditions at early times. This is the behavior on super Hubble scales at late times for a mode that emerged from inside the Hubble radius during ultra slow roll inflation. Now there is a transition to ultra slow roll. So the Fk changes. Let us say it changes abruptly at some time eta 1. Okay? And I will let you convince yourself that K by A, K equal to AH is Hubble exit. Okay? So if a mode, this mode K1 will leave the Hubble radius at eta 1 in d sitter. I will let you show that. So if the transition occurs at eta 1, then on super Hubble scales, right, during ultra slow roll, the behavior is Z is different. I can write it in this. Okay? There is a constant solution, but there is a growing solution. Remember, eta goes to 0. Okay? And what I need to do is that there is a mode which has left the Hubble radius, okay, and is entering this epoch of ultra slow roll. And you can match AK and BK to CK and DK. I haven't indicated what DK and CK are, but they can be determined by imposing the Bunch-Davies initial condition. And you can evaluate the power spectrum at late times, at some late time eta 2, which I have called as 1 over minus 1 over K2. I am assuming d sitter at all times. Then the power spectrum happens to be this form. So what do I have? I have an epoch of slow roll followed by an endless epoch of ultra slow roll until some time eta 2. Then what you obtain is a spectrum of this form. Remember, K1 indicates the time of the transition. K2 is the time that when I evaluate the spectrum. You can consider two scenarios where K is much, much smaller than K1, right? So all these modes have left the Hubble radius at very early times, okay, during the epoch of slow roll. Then the power spectrum is K power 0. Then you can consider a scenario where K is much, much greater than K1, okay? I will let you convince yourself. In fact, 6 squared is 36. 36 by 288 is 8, 1 over 8. And therefore, on small scales, on small k, the spectrum is essentially what you obtain in slow roll. But on large k, k greater than K1, what you show, I will let you show it grows like K power 4. So if you have an epoch of slow roll followed by an epoch of ultra slow roll, you will have a spectrum that is flat, and then there will be a sharp rise like K power 4. But of course, if you see these inflationary models, not only do you have an epoch of ultra slow roll, there is, epsilon 1 rises to leading to an end of inflation. So you have to model that part as well. So at eta 2, where I have evaluated the power spectrum, you need to make this transition to another epoch. Okay? And you can do that. Okay? I will come to this picture in a few minutes. So I have an epoch of slow roll. I can have an epoch of ultra slow roll where the epsilon 1 comes down, and then there is an epoch where epsilon 1 rises, as you can see here. I've chosen to rise, make it rise in a particular fashion, okay, here. And there are two epochs. Epsilon 2 is 0, slow roll, ultra slow roll, and there is a rise in epsilon 2 leading to the end of inflation. What is amazing is that in all these cases, you can solve for the Vk, the Mukhanov-Sasaki variable, exactly. Okay? And Z double prime happens to be in the initial slow roll regime, 2 by eta squared in the ultra slow roll regime, and 6 by eta squared. And I told you, remember, 1 over eta squared implies Bessel functions, and if this is 2, it is h3 by 2, and if it is 6, it is h5 by 2. All these are simple functions, and you can write them. So the initial first phase, second phase, which is h3 by 2, this is h3 by 2, h3 by 2, remember, okay? And this happens to be h5 by 2. And you can match them, determine alpha k, beta k. These are just the Bogoliubov coefficients you may have encountered. And you can evaluate the spectrum at late times. So what do we have? We have slow roll, ultra slow roll, and then a period where epsilon 2 rises leading to the end of inflation. So I'll come to the spectrum in a minute, okay? I will take a minute or two to explain this. So this is a numerical result. What has been plotted, this is the period where ultra slow roll comes in, sets in. There is slow roll prior to this, and there is this brief epoch of ultra, not quite slow roll leading to the end of inflation, okay? That is, this corresponds to this regime where it rises like this, okay? And so notice this is epsilon 1. This red curve is epsilon 1. It rises, falls during this epoch of ultra slow roll and rises again. Epsilon 2, the modulus of epsilon 2 has been plotted because we have a log plot. So this is very small. It's close to -6. It's like 2 or something, like I had modeled in the analytical result. If you have a mode which left the Hubble radius at very early times, then what happens is that, it comes down and settles down at this amplitude. If it has left even earlier, it comes down and settles that amplitude. But consider a mode that leaves either just prior to ultra slow roll or during the epoch of ultra slow roll. Here is a mode that leaves the Hubble radius during the epoch of ultra slow roll. Notice, until Hubble's exit or so, it comes down here. And then notice this rise in amplitude, right? Rise in amplitude and settles down. So essentially what happens is that, the growing mode during slow roll was a constant. The growing mode during ultra slow roll actually grows, and it flips to that growing mode, and its amplitude ends up here. And that is why these modes which leave during the epoch of ultra slow roll have significantly larger power. Where is the power spectrum? Okay, so these are modes that leave the Hubble radius during the epoch of ultra slow roll or just prior to it, and they have significantly larger power. Let me come back to this analytical example. So you match these cases, okay, and these are the epsilon 1, epsilon 2, and epsilon 3 for these cases. And this is one of them is the numerical result, whereas that, the analytically evaluated quantity is in blue. This doesn't match very well. You need to change parameters, but you have a scalarity and you have a rise in power, you have a peak, and you have a fall in power, much like you obtain in these various analytical models. So if you have potentials which have a point of inflection, you can ensure that they lead to significant power on small scales, and there are many such potentials that have been constructed in the literature. Let me just quickly discuss some consequences in the 5 minutes I have. Cristiano will correct some of these discussions. Okay, one of the quantities, as I said, of interest is the fraction of primordial black holes that contribute to the cold dark matter density. It is often used, often a standard formalism is used to calculate this FPBH. Cristiano will discuss in some detail, and and there are some important differences, and it's also sensitive to parameters involved, and based on certain numbers you can estimate on certain models, you can show that they correspond to, for instance, if this FPBH is 0.1, it essentially implies that 0.10% of black holes, cold dark matter in the universe is in the form of primordial black holes. There are strong constraints, relatively strong constraints, and they are improving as we speak, okay, on the FPBH. But there are windows, the so-called asteroid window, where they can, in principle, you can have primordial black holes of these masses here, 10 power minus 16 solar mass or so, and they can, in principle, constitute all of dark matter today. Of course, the challenge is to first check whether these estimates of primordial black holes, number of primordial black holes, are correct, which is what Cristiano will talk about. And of course, there are models, whether you can have models that lead to the peak of this regime without violating any of the other observational constraints. Since in the next 2 minutes, I will just discuss another possibility. I will not have time to discuss these in detail. So let me just flash a slide indicating what are the possibilities. Earlier, I talked about the spectral energy density of primary gravitational waves. Remember, what was their amplitude? If you had an instantaneous transition from inflation to radiation domination, I said they will have an amplitude of 10 power minus 17 or so, and they will essentially be straight. And they will be far below the sensitivity curves of many of the ongoing and forthcoming observatories. If you had an epoch of reheating, with the equation of state greater than 1/3, some of the primary gravitational waves can rise and can become comparable again to the sensitivities of the gravity wave observatories. I had also said one more thing, that at the linear order and perturbation theory, right, the scalars and tensors evolve independently. But you can ask what happens at the higher order in perturbation theory. And you can show that quadratic order in scalars, okay, scalars at the quadratic order can induce gravitational waves. These are called secondary gravitational waves. If you had slow roll inflation, the strength of the secondary gravitational waves should be less than the strength of the primary gravitational waves. That's the hierarchy of what you expect in slow roll inflation. So if you estimate the energy density, spectral energy density of secondary gravitational waves induced by the scalar perturbation, they will be smaller than 10⁻⁻17. And they indeed, that will correspond to the curve somewhere here. They will be of the order of 10⁻⁻23 or so. Okay? If you had slow roll inflation. Remember, these are induced by scalar perturbations. In slow roll inflation, the amplitude of the scalar perturbations is 10⁻⁻9 or so. But if you have scenarios where you produce enormous number of primordial black holes, the amplitude of the scalar perturbations are significantly higher. And these scalar perturbations can induce secondary gravitational waves which are much stronger peaks than the primary, stronger amplitudes than the primary gravitational waves. And it is not surprising that since the scalar power spectrum has a peak, there will be a peak in the spectrum of secondary gravitational waves corresponding to those wave numbers where there are peaks in the gravitational wave power spectrum. Scalar power spectrum. So if you end up producing primordial black holes, significant number of primordial black holes of certain masses, there will be corresponding peaks in the spectrum of secondary gravitational waves. And they happen to be comparable to the sensitivities of the ongoing and forthcoming gravitational wave observatories. In fact, one of the most popular model which fits the data fairly well to explain the PTA data is indeed a primordial power spectrum of the type that I have considered. You just have to produce them, at this scale, and they happen to fit the data much better than this popular astrophysical model of merging supermassive black holes, binary black holes. With that, I will just summarize. These are standard comments related to gravitational waves, and I will let you read them. And before that, I'll just show you some references. It's an advertisement for some of my own work, so you can read these reviews, and there are many other reviews as well. You are welcome to, write to me for a list of them. I will be glad to provide them, and I will let you read the summary, and I'll be glad to answer questions. Thank you.